Welcome class to the very last lesson of this discrete functions chapter 6. We're going to be looking at geometric series. You should have a pretty good grasp of the arithmetic series formula at this point and the concept of a series, which is the sum of sequence terms. And in this lesson, we're going to be looking at a really interesting example from history. It could be a legend, could be true, that is going to be used to introduce the formula. And what I'm going to do is play a video shortly, and then this will get you started for the challenging question, which is, which would you rather get as a prize if you were in a game show? 1 million gold bars or a chessboard filled with grains of wheat as follows: 1 grain in the first square, 2 grains in the second square, 4 grains in the third square, 8 grains in the fourth square, etc. And clearly the pattern there is just doubling. And in case you're wondering, there's 64 squares on a chessboard. So if you want to try to work out a pattern, maybe determine the number of grains that would be on the very last square, that's something you can look at as well before you watch this video clip.
This is an old story, but it reminds us of the surprises we can get when even a small number like 2 is multiplied by itself many times. King Shahram of India was so pleased when his Grand Vizier Sissa Bendar presented him with a game of chess that he asked Bendar to name his own reward. The request was so modest that the happy king immediately complied. What the Grand Vizier had asked was this: that 1 grain of wheat be placed on the first square of the chessboard, 2 grains on the second square, 4 on the third, 8 on the fourth, 16 on the fifth square, and so on, doubling the amount of wheat on each succeeding square until all 64 squares were accounted for. When the king's steward had gotten to the 17th square, the table was well filled. By the 26th square, the chamber held considerable wheat, and a nervous king ordered the steward to speed up the count. When 42 squares were accounted for, the palace itself was swamped. Now fit to be tied, King Shahram learns from the court mathematician that had the process continued, the wheat required would have covered all India to a depth of over 50 feet. Incidentally, laying this many grains of wheat end to end also does something rather spectacular. They would stretch from the Earth, beyond the Sun, past the orbits of the planets, far out across the galaxy to the star Alpha Centauri, 4 light years away. They would then stretch back to Earth, back to Alpha Centauri, and back to the Earth again.
Okay, now that you've seen the video, here's what we want to do, is try to figure out mathematically how these two amounts compare. They seem to be pretty lopsided. We've got wheat on one hand, which is a commodity and has value, and then we have 1 million gold bars on the other hand, which is also a commodity and has a lot of value. And just to give you a little bit of background here, there's some information which we need to gather to solve this problem. One of the pieces of information is, what is the mass of a gold bar? So in order to determine that, we're going to need to go to some websites, and the first one we'll go to is the US Mint website. Okay, here we are. Now this is a fact page from the United States Mint, and a little bit of background. The storage facility for gold holdings in the United States is at Fort Knox in Kentucky. The amount of the present gold holdings as of this current web page was 147.3 million ounces. And the most that has been held since this holdings location was in operation this century was almost 650 million ounces. And on this fact page, they also give the weight or the mass of a standard gold bar at approximately 400 ounces. And so what you really could look at is 1 million gold bars would be really a little bit more than what is currently being held at the Fort Knox gold holdings. So that's a lot of gold. All right, now at this point, let's try to figure out what the current commodity price is for gold. All right, here we are at the Commodity Price Monitor from the Royal Bank of Canada, and this web page provides lots of graphs and different index values on the financial markets, and then we start to get into the indices, and those are benchmarks for economic growth and economic health in our country. And then we start the commodity price trends. And so for wheat, which we'll also be interested in, you can see the graph and the trend for the price of wheat over the last 8 or 9 years. And then we get to the actual data charts a little bit further down. All right, and if we find gold, it's under precious metals. And here we are, gold. Currently in 2015, our price per ounce is $1,178.60. So we're going to use that figure as the current price per ounce, $1178.60. Okay, going back to Wikipedia, we need to know how heavy a gold bar is. So a gold bar, also called a gold ingot or gold bullion, is a bar that has a mass of 400 troy ounces, but the standard ounce, the amount is 438.9 ounces. That's called a good delivery gold bar. So 438.9 ounces is the mass that we will use. Okay, the last commodity price, which I'm going to grab here, is for wheat. US dollars per ton as of March 2015 was $282.70 for a ton of wheat, $282.70. Okay, and continuing on, there's one more piece of information which we need, which comes from an article that I located on an agriculture website, and this is a standard value which the agricultural industry uses for the mass of 1,000 grains of different types of wheat varieties. And in the abstract and in the introduction, we can see here that the average mass for 1,000 grains of wheat is 38 grams. So we're going to use that as our average wheat grain mass, 38 grams for 1,000 grains. Okay, so we've gathered all of our information, and here we're looking at, all right, what do we do with all this? Well, we want to find out the value of the wheat and the value of the gold, and there are some details missing here at this point. One is, what is a ton? Because we need to be able to somehow convert the total mass of all these grains of wheat on the chessboard to tons if we're going to calculate the value of the wheat. Well, a ton is 1,000 kilograms, or it's 2,000 pounds, depending on whether we're talking about a metric or an imperial ton. A metric ton is 1,000, and an imperial ton is 2,000 pounds. Well, if we go with the US ton, 2,000 pounds, we would also need to know that 1 pound is 354 grams. So that would help us convert mass of wheat in grams to pounds to tons, and then we can calculate the cost or value of that wheat. The amount of money associated with the gold is a little bit easier to calculate because a gold bar is 438.9 ounces, and we have the value there. So the only thing missing is we have 1 million of those, so some calculations linked to that as well. Well, before we go ahead with this comparison, this cost comparison, I'm going to just take a bit of a detour and look at how would we calculate the number of grains of wheat. This is the real variable here, it's unknown. And the reason why it's unknown is because, well, we do know that on a chessboard, we're going to have 1 grain of wheat on the first, 2 on the second, 4 on the third, 8, etc. But by the time we get to the 64th square, we need to follow a pattern here. 1 is 2 to the 0, 2 is 2 to the 1, 4 is 2 squared, 8 is 2 cubed. This is just following the geometric general term, AR to the n subtract 1, where the first term is 1 and the common ratio is 2. And so, for example, 8, which is term 4, is 1 times 2 to the 4 subtract 1, or 2 cubed. Okay, so that fits. All right, that's important because the 64th square is our last term. We know there will be 64 numbers that we have to add, and that means it should be 2 to the power of 63. But all that tells us is that on the 64th square, that's 2 to the power of 63 grains of wheat, which is still an awful lot of wheat. And on the 63rd square, we would have 2 to the 62. But the thing is, we have to add all these numbers up, and that means we need a series. So let's take a bit of a detour, and we're going to look at the proof for the formula that gives us the sum of a geometric series. All right, at this point, you should have this handout if you're following along with this lesson. And the back page of the handout, the second page, has you studying copying the derivation with the documentation as far as what's going on there. This is from page 403 in your textbook. So I've already completed the derivation. I'm just going to show the steps. The first thing we need to recognize is that a geometric series is the sum of the terms of the sequence added together. There are going to be n terms. The first term will be a, the second term will be a times the common ratio, the third term will be a times the common ratio squared, and all the way to the very last term, which is the nth term. It'll have the form ar to the exponent n subtract 1. So it will have a power where the exponent on the common ratio is 1 less than the number of terms. Well, that makes sense. What about the term before that? Well, that would have an exponent which is 1 less than that, because the common ratio has been multiplied 1 fewer times. What is 1 less than n subtract 1? Well, it must be n subtract 2. So although we're not showing every term here in this series, we're certainly showing what the pattern is. The way this derivation works is to take that sum and multiply it by the common ratio. And the reason why we do this is because what it actually does is it produces a second series which has the same number of terms, and almost all of them except 2 have the exact same value. And so if we put those together and we subtract the series multiplied by the common ratio from just the series, what we end up with is everything cancels out, and all we're left with is the first term subtract this term. And what would that look like? Well, it would be the sum of the series subtract r times the sum of the series would give us a subtract ar to the n. What I'm going to do here is just help you focus on just this one part. Okay, so the next step here would be to common factor. The sum of the series is the sum of n terms. We're going to common factor that from our 2 terms. That will allow us to solve for, isolate our sum of n terms of the series as follows. The restriction on this is important. We don't have a geometric series if our common ratio is 1. So that also fits with the fact that the denominator can't be 0, and r equals 1 would make that true. So it's consistent. The math is consistent. What we know about domain also lines up here with what we know about what a geometric series is and what it isn't. The alternate form is the one you'll see in your textbook, and this is obtained by simply taking this version here, which has been shown in green, and just basically taking the opposite of the factor in the numerator and the terms in the denominator. And what that allows us to do is cancel out this -1 factor from both numerator and denominator, giving us a slightly different version, but basically amounts to the same values. So this is the one that we'll probably be using in our calculations more often, and it also has the same restriction. All right, so from here we could go back, and now we can tackle this question that involved the number of grains of wheat. Of course, now it seems very simple. We have a geometric series where we're adding 1 and 2 and 4 and 8 all the way to 2 to the 63. We know there are 64 terms, We know the first term is 1. We know the common ratio is 2. So we have all the information needed to calculate the sum of 64 stacks of grain, wheat grain. So this is going to be, as we had just demonstrated, the derivation was as follows. So we can substitute in what we know. First term is 1, common ratio is 2, there are 64 terms. Divide that by 2, subtract 1, and this is the sum of those 64. So you need a calculator for this, obviously. 64 as a power of base 2 is a very large number. And the thing is, when you subtract 1 from that, you're really not doing anything to it, or very little to it. So this is almost equivalent to 2 to the 64 all over 1 in the denominator. Keeping in mind, as I said, reducing that really, really large number by 1 doesn't affect it very much at all, and certainly doesn't affect our total sum much at all either. So this is, all right, the number of grains of wheat is 2 to the 64. Just kind of an interesting little outcome that all of those numbers really add to the 64th power of base 2. All right, now that loads back in here as 2 to the 64. This was our unknown. And now we can start tackling the value of all this wheat. So let's figure out how many grains and how many tons we have. We know that it takes 1,000 grains to get 38 grams. All right, so I think what I would do at this point is I would try to determine how many thousands is 2 to the 64. So what we're looking at is the number of grains in thousands. So we divide that by 1,000. So that's going to be 2 to the 64, and 1,000 is 10 to the 3. And if we take 2 to the 64, divide by 1,000, we get a very large number, which again, we're going to have to kind of keep track of these numbers using scientific notation. So this is 1.844674 times 10 to the 16. So that number, all right, here's our answer. For thousands of grains, we have this number, which we'd have to understand represents so many thousands. Now, the reason why I'd be trying to get that is because each 1,000 quantity of grain, 1,000 kernels or 1,000 grains of wheat represents 38 grams on average. So what we're looking at is a mass, getting closer to our value for the wheat. The mass of wheat equals 38 grams per 1,000 grains multiplied by this number, which is multiples of thousands. Okay, and that's going to require a calculation, so we'll work that out. All right, so our answer here is shown. This is going to be a mass of wheat in grams. Now, looking into the ton a little bit more, I discovered that when ton is spelled T-O-N-N-E, this is a metric ton, and this is exactly 1,000 kilograms. So this is, although it's the commodity price came from a US dollar, we're still going to go with the metric ton. Going back, originally we had recorded $282.70 per ton. So we just need to figure out how many kilograms we have of wheat and how many tons that corresponds to. So going back down here, we need to take our mass now and convert it into tons. We're going to take this number and multiply that many grams by 1 kilogram for every 1,000 grams. And then we could sort of think about maybe one more conversion factor, which would be 1 ton for every 1,000 kilograms. So I'm using a couple conversion factors here, or ratios, which, as you might have seen in science courses, allows for simple conversion of units, as long as we know the rate to apply. And so this calculation really just requires us to take our mass in grams and divide by 1,000 thousandths, or millions. That's what I'm going to do here. All right, our solution moves forward. We now have reduced our mass of wheat by a factor of 10 to the 6, or a million. And this is going to be tons now. So we're getting really close to calculating the value of the wheat, which is our final answer. So the value of the wheat is going to be number of tons multiplied by the cost per ton, which was, I believe, $282.70 per ton. And if that's in US dollars, then US dollar value. So one more calculation here. All right, so this is our final dollar amount, and this is on the order of 10 to the $14. So it's a big amount. We're looking at trying to make this a little bit more within our realm of understanding. So 10 to the 14 is hundreds of trillions. So we're looking at, this is 1.9816,599 times 10 to the 2 times 10 to the 12 US dollars. So big amount here. This 10 to the 12 order of magnitude would be trillion. And this is about 200. So that means that if we had taken that offer of 1 grain of wheat on the first, etc., we would eventually, after having collected all those grains of wheat and cashed in, we would be looking at approximately 200 trillion US dollars. That's a lot. All right, now at this point we'll go back and look at the gold, and then we'll wrap up. All right, well, I've had some fun with this activity. I hope you have, and we've been exploring some business applications. So I'm trying to make this a bit cross-curricular, but this last calculation is much simpler. We have the bar mass of gold, 438.9 ounces. We have the unit price per ounce at $1,178.60 US dollars, and then we have our million gold bars, almost what would be found at Fort Knox in Kentucky currently. And the final value of all of that gold, believe it or not, still comes shy of the total wheat value. And it's interesting how close it is. I think when I designed this activity, I wanted to make it close, and it is pretty close. The question would be, what would you do with all that wheat? But the again, the amount here we could probably work with is this is 5.1728754, which we'll just call approximately 500, and 10 to the 9 is billion. So this total value of gold comes in at about $500 billion, which is a lot of gold, but it's still a little short of the 200 trillion US dollars of wheat. All right, well, let's just come back to the back of the worksheet and, again, review that formula. We've applied it once at this point. The remainder of the exercises to play out tomorrow will be sample problems, to have a look at those and see me in class if you don't understand. Have a look at the Communicate Your Understanding questions on page 407, and in class tomorrow we can discuss with a partner. And the worksheet goes on to outline practice problems from the handout, as well as the feedback problem and portfolio question. I'm just going to use the remainder of the video lesson time looking at a couple of questions from the Blackline Master just to give you a start so that you come in tomorrow and you've seen the formula used a couple times more. Okay, I chose to look at a couple of questions on this Blackline Master. Number 2, determine the sum for each given geometric series. So no context here, just looking for right off how many terms there are. We need the first term, we need the common ratio, and we have the last term, which we've seen before is often introduced in the problem to get us to use the general term formula to find the number of terms. And that's what we're going to have to do here, is just going to restate the sequence as a series showing that this is all sum. I'm going to choose part C to look at. And even though the signs are alternating, we're still adding terms. Every other term is negative. And you can see the common ratio here is actually just a half, negative a half, that is. So I'm going to list what we know. We know the first term is 100, the common ratio is negative 1/2. The nth term, or the last term, is 25/16. We don't know how many terms are in this sequence. So we can express the information that we know so far as using the general term of a geometric sequence. So I hope you haven't forgotten that. A/r to the exponent n subtract 1. Got to be careful when you're memorizing these formulas. This looks a little bit like the sum formula, which is a with a bracket, r to the n, and subtract 1, not in the exponent. So just study those out and just make sure you can tell them apart. And we're going to take that last term, 25/16, and set it equal to 100 as the a, multiplied by the r to the n, subtract 1. And I'm just going to go through the solution here. I've already worked it out, and you can just follow along. So for the first couple steps, all I'm just doing is just separating the left side into a fraction with a base of negative 1/2. I hope you can see that 1/16 is negative 1/2 to the 4th. Now what I'm trying to do here is work both sides until I can get a common base. And after a couple steps, I realized that having 1 and 4 on both sides didn't really help me get to a common base of negative 1/2. So what I decided to do is switch to a base of 2. And you'll see in this couple steps here why that's going to be helpful. So negative 1/2 is, and I'm just picking up on a mistake I've made here, would be negative 2 to the negative 1. And likewise on the left side, there should also be a negative in front of that. Keep in mind, 2 to the negative 1 is 1/2, which means that negative 2 to the negative 1 would be negative 1/2. That little mistake I made, I realized isn't going to really affect anything because it's the same mistake on both sides, and so it's going to kind of cancel itself out. I could really take both sides and divide it by negative 1 and they would become positive. Alright, so as you're following along here, just keep in mind, trying to get a common base so we can solve this exponential type equation. So 2 to the negative 4 on the left side, and now what you can see, I've taken the 4 and I've made it 2 squared. And now the convenience here is that 4 is base 2 and so is 1/2, and I can apply the product rule of exponent laws. So I'm going to really take my two exponents, which are 2 and negative n plus 1, and that came from power of a power applied right here. And so negative n plus 1 is going to get added to 2. So negative 4 equals 3 subtract n. Now this is a fairly long way of solving for this, and I think some of you might have gone about it a little differently, but I chose to do this just to show you how to go about solving an exponential equation when you don't have the exponent. And you can use that strategy of trying to achieve a common base, and once you have a common base, then the exponents have to be equal if the bases are equal. So it's pretty easy to solve that equation. If the exponent is equal, then negative 4 equals 3 subtract n leads to our solution of n equals 7. Now all that for the purpose, of course, of getting the number of terms in the series. So the rest of it is just working out the sum, which is a r to the n subtract 1 all over r subtract 1. And I've just shown in parts here to remind you, got to be careful when you're calculating this. Order of operations is involved, and I would suggest you evaluate your r to the n subtract 1 as a separate value, and then work one extra step in your solution, which would be this one right here, before you get to your final answer of 67.1875 is the approximate answer for that sum of 7 terms. Okay, and this last problem For this lesson, just is going to go through a lottery prize distribution. So the first prize is $400,000, and every prize after that is 40% of the previous prize. So the question tells us there are 5 prizes, and we're trying to determine the total amount paid out. In this case, we're going to look at just listing these prize amounts as a sequence. So we have the given information, 5 terms, 5 payouts, 400,000 is the first one. The common ratio is 0.4. So we can just substitute all that information in to our sum of the series formula. We don't need to know, in this case, the last term, because we're told that there are 5. So that's the nice thing about the sum of series formula, is sometimes all we need really is just N, A, and R. And again, here, just substituting in what I know, showing that extra step. This just take note of, you have a negative term in the denominator, so you can expect that you'll have a negative term in the numerator to offset that, to give a positive payout amount. And the final value of the payout is $659,840. And I confirmed this by adding up 5 terms according to the pattern in our sequence. So that last example should give you an idea what you can do with geometric series. See you tomorrow.